Okay, welcome to the third lecture. So this will be a lecture about Introduction to Circular Economy. Before we go to the lecture, I have to mention a couple of things. One thing is that last time with the homework, maybe the forum wasn't great because some of you emailed me that you weren't able to submit your homework. So I would work on proposing a different forum or a different method to actually give your homeworks. The idea is not that people cannot see each other's homeworks, but you can actively actually see each other's inputs and then have a dialogue or a discussion on these things. So maybe I will try to open a discussion forum within University Virtual, and then you tell me if it works well or not. Maybe there is an option to go to Padlet. We will see which one works for us better. Okay. So usually the circular economy lecture may begin with the famous butterfly diagram from the Ellen MacArthur Foundation. But I have to say we can take a different approach here. One thing, the way I start the definition of circular economy is to look for scholarly definition. There are different types of approaching a concept. You have the practitioners' definitions. The people who practice it can put forward some definitions. There are people in businesses, they could put forward some definitions. But for any concept to last long, we should look for solid scholarly definition. If I ask you what the first, second, or third law of thermodynamics is, you would be able to, of course, define them in concrete terms. If I ask you to define what is a circular economy, that's going to be a challenge because there is a review paper where they review 114 definition of circular economy. People call it an umbrella concept, embracing so many different concepts inside its umbrella. People call it an essentially contested concept. If you are a sociology major listening to me, you already know what an essentially contested concept is. If you don't, maybe Google what an essentially contested concept is. I will also upload the paper where they call it. It's not a bad thing. It's something that, let's say that it is something under debate, and there are a lot of important additions to it that has to be made from a critical angle so that it can be made into a solid concept is what essentially it means. And then you have people who criticize it as CE bubble, the circular economy bubble, and people call it deliberately vague. All of this are quotes I am giving you from articles and research papers. So you obviously know it's important and serious thing to define the circular economy. Let's go to one particular definition. So the people who analyzed 114 definitions of circular economy came to this definition of circular economy by synthesis and iteration. Okay, they have this coding framework. They defined CE from multiple various definition where you have to pay attention to this whole paragraph carefully. It is an economic system that replaces the end-of-life concept with reducing, reusing, recycling, and recovering materials in the production/consumption processes. The other thing that you have to notice here, it operates on the micro level, meso level, and macro level with the aim to accomplish sustainable development. So there are multiple different levels here. What does it mean? It simply talks about the scale. The scale is different. For macro, it could be the country, it could be a city, it could be even on a planetary scale. For micro, it could be to the level of the product. Okay, so you have to always take this into consideration. Circular economy is not simply about making a product circular, but there are different levels to it. And then simultaneously creating environmental quality, economic prosperity, and social equity, not just for the current, but also for the future generations. So here in itself, I can tell you that there are many different angles to circular economy. Some people emphasize on the environmental quality. Some people even ask, is economic prosperity the important goal, or actually saying human well-being the important goal and human dignity the important goal. So there are constant debates and dialogues going inside the CE community, and we need to be cognizant of that fact, not take simple definitions, but embrace or understand circular economy with all its complexities. Okay, the way I propose that we approach circular economy is by this way, not by definitions, but by understanding what gave rise to it, by its historic origins, by the diversity of the school of thoughts that actually gave rise to circular economy. You have the eco-design, you have the renewable energy, which are supposed to be a key part of circular economy. You have what's called as the performance economy. You have industrial ecology. Industrial ecology is a serious academic field. It's not a concept that is put forward in the context of circular economy. It's an academic discipline, and you even have master's courses and multiple PhDs in industrial ecology. And then you have the concept of industrial symbiosis. It is a part of industrial ecology, one could say, but it also has its own set of principles. Then you have what's called as a social economy, and then you have the very famous butterfly diagram. And then you have biomimicry, cradle to cradle, blue energy, and multiple other things. We are going to see eco-design maybe in the next part of the lecture, maybe not for today, in the forthcoming week. So let's put that aside. And in the case of biomimicry, I think I can share you the links. You are going to read it by yourself. The other things I'm going to touch and talk about in a little bit more detail. In fact, we are going to open up with industrial ecology, industrial symbiosis, and so on. And the butterfly diagram is not going to be in this lecture, but the next lecture that I'm going to upload, where we will talk about recycle, repair, remanufacture, etc., together with the butterfly diagram. So let's think about circular economy as a part of different schools of thought and understand what those schools historically thought about and what they wanted to achieve and how it integrates with the current idea of circular economy. So let's get into the world of industrial ecology. Industrial ecology is a serious academic discipline. It has its origin on many different things, which we will see in a jiffy in the next slide. But the first article was published in 1989 in the magazine Scientific American by Frosch and Galopoulos. So this was really a seminal article. It was titled Stages in Manufacturing, or Stages of Manufacturing. But in fact, the authors have actually titled it as Manufacturing, an Industrial Ecosystem View. The journal rejected it, but it's an interesting part of the history. But you could see that how industrial ecology concepts have evolved over time in this slide. It has various different components. Essentially, it has three different parts. First is an analytical part. Industrial ecology tries to analyze how industrial systems function. And then you have a methodological part where they have these materials and energy flow analysis and life cycle analysis, where they want to kind of quantify the impact of these industrial systems on the biosphere. And then third, they have the part where essentially the motive or the objective is to change how things work. So you can broadly divide the functioning of industrial ecology into these three things. Now you could see over the years how things have changed. They say it is a rational approach, and it is an approach that is, how to say, in synchrony or harmony with the Mother Earth system. And then also it talks about reduction of overall impact on the environment in a totality. But also notice the fact that you have a lot of words about closed loop system and diversity and locality and change, etc., because it's going to be useful when we go to the next slide. So as I was talking about, Industrial ecology drew inspirations from many fields and has many integral concepts to it. So you have first, as we have already seen, the linear system in which you have unlimited resources and you could take it into a system and produce unlimited waste, which is obviously undesirable. They took inspiration from biological analogies. So you have these biological ecosystems, and you could take on a planetary level or on a smaller level like a rainforest. So you always have, let's say, plants having photosynthesis and producing its own food, and then plant becoming food for one animal, and then that animal goes on to become a food for another. So this is like a closed cycle of flow of nutrients, let's say. So this view of having loop closing is something they took from biology. The waste of one component in a system always becomes a food for another entity in a system. So the waste is equal to food concept is something that is inherently present in biological ecosystems. On a really longer time scales, it's almost perfect. They always have a perfectly synchronous cycle, a lot of biological systems on a local or even on a global scale. And then you also have this concept of diversity through resilience. So for instance, industrial ecologists use this resilient concept in many different manners. I will give you an example much later in another exercise when it comes to metal criticality. But essentially it is this. You have, let's say, a disturbance to a biological ecosystem. It recovers from the disturbance or the perturbation through its diversity. So, for instance, due to the presence of many different type of organisms, even through natural biodiversity loss or so, it could actually cope up and then still have the ecosystem intact with a lot of resilience. This it is possible to do due to the diversity. So that is something is also taken into account by industrial ecology. And then you have what's called as a systems perspective. Always think in terms of holistic industrial ecosystems. And that is where the concepts of life cycle analysis, materials flow analysis, and energy flow analysis, and all of this comes in. So only when you take not just as parts, but as whole, you could avoid unintended consequences. Then industrial ecology has a component where they believe that where it is emphasized that technological change or technological advancements are integral part in solving sustainability puzzles. You have this famous IPAT equations. We are going to see a bit more in detail in the module of recycling, but it is essentially this. It's an entity which says that the environmental impact is equal to population times the affluence times the technological advancements. So simply do it mathematically, you would get an idea. Imagine in, let's say in 50 years, the population grows by 4% and the affluence, the GDP per capita increases by 5 times. What you want to have is an advancement in technology so much so that the environmental impact in 50 years remains the same as it is now. So you have to have the improvement in the technological part. That is, the environmental impact per unit of GDP should be really radically reduced so that the total impact remains the same. So the T part has to really improve. Just make a mathematical assumption of the increase in population and affluence and see how much the technology has to improve, so you will get a grasp of it by yourself. And you have the components of dematerialization and eco-efficiency. So dematerialization is something that we already talked about in material footprint. So reduced resource consumption, reduced material consumption with the performance of a similar or almost the same performance in a product is what industrial ecology advocates. And also eco-efficiency, increased efficiency of products and systems. And there is a component of forward-looking research and practice. That is, you have to take into account the innovations, the disruptions that comes into account and have an outlook where this can be implemented constantly. So it is not a static study in essence, it's very dynamic. Then we go into the concept of industrial symbiosis. So what is industrial symbiosis? It's something defined by Foch and Galopoulos much earlier, even as early as 1989. The consumption of energy and materials are optimized in such a way that you have minimization of waste generation, and the effluents from one process serve as a raw material for another. You already see that the waste is equal to food concept coming into play here in a symbiotic way. So a lot of it is biological metaphors, let's say. Industrial symbiosis, by definition, applies the ecological metaphor of industrial ecology. You could say that it is a branch of industrial ecology, but a specific one at that. It creates a collective approach for firms and industries traditionally viewed as almost independent entities, and considers the entire system with regard to the exchange of materials in terms of its energy and byproducts. So we are going to see some concrete examples, or one concrete example of industrial symbiosis in this lecture. So this is not the example we are going to see, but it is the most important example that is really widely researched, because it is one of the earliest industrial symbiotic implementations, let's say. Even almost before the concept came into existence, the Kalundborg symbiosis in Denmark really existed, and you could see the different flows of energy, water, and materials between different plants inside an industrial ecosystem. So this is something you could go and read from different parts in the internet about the Kalundborg symbiosis in Denmark. It is one of the original and foremost important systems that is actively researched. But the thing that I'm going to talk about today is an EIP in China. EIP is an Eco-Innovation Park. Already you see one thing you have to take into account. Eco-Innovation Parks are on a different scale. So you can have multiple types of industrial symbiosis. Industrial symbiosis typically is defined between a really closed geographical entity, but it could also be on a larger scale than a geographical entity for a country, between countries. So it is the boundary of industrial symbiosis is an interesting thing, and by boundary I mean the scale. So we are going to take a look into an example of an eco-innovation park in China. So first, the researchers who did this research, they actually did it for policy and how policy influenced such eco-innovation parks. That's not what we are going to go after today. We are just going to see what happens. So first, they took a system boundary and reference year. The system boundary is obviously the physical boundary of the cluster they are researching in. You see, they also take a reference year because, as I told you, industrial symbiosis, like as industrial ecology, is dynamic, because not every year, over a period of time, you have different types of dynamic interaction. Even in Kalundborg symbiosis, you could see some of the plants which were original are not existing anymore, but still the symbiosis keeps going. So you could see over the years there are many innovations replacing the symbiotic processes. And then you have the industrial symbiosis identification, in which you have the byproduct exchange. More than 90% of what happens in IS in this case is exchange of byproducts. The waste from one becomes food for or feed for another. And then you also have infrastructure sharing. Maybe the companies or industries have similar goals, and you could share the infrastructure and take all the feeds to get to a point where you want to achieve some end goal. And then you have to always have the quantitative things in inventory. You have to quantify the inputs, you have to quantify the outputs, the wastes in all different forms. You have to quantify flows, not just stocks, but also flows. Flows is a measure of something over a period of time, and then you have to measure that as well. And then you have to rigorously collect the data. You can interview, you can question people, and you analyze the performance, and you detail the benefits of industrial symbiosis performance. It could be that you have a reduced material or a carbon footprint. It could be that you have a really closed connection, that you don't need raw materials from elsewhere anymore, and then they have sort of results and discussion. So here they have a park called as Reida in a province in China, and on the left you see the industrial symbiosis from particular years, from 90s to 2000s, and then 2003 to 5, and then 6 to 11. On the right is more juicy and industrial and important part. You see here they have this textile industry, where the sludge from that industry is used instead of calcium carbonates in the factories of citric acid. And then you have the production of the waste of fly ash and green mud, which is used immediately to produce cements and other types of building materials. And you have the sludges being used as organic fertilizers, water molasses, waste molasses used instead of cassava to produce alcohol, and very interestingly, the metal scraps at the bottom, you could see they are all collected in a metallurgical plant, and then they are smelted, and then they are recycled. And you have the reclaimed water being reused in a thermoelectric plant, and many other examples. You could see that 90% of what's happening in industrial symbiosis plant is actual exchange of byproducts. And then you have also the sharing of infrastructure between companies, which reduces the load as well. There is also, they say, a possibility to have water and material flows. Material flow obviously exists, water flows, but this was difficult in this particular case due to constraints in the infrastructure. So this is in essential a nutshell how an industrial symbiosis plant works. You see again the concept where they have many things from industrial ecology emphasized here. You need to have a systems perspective. You just cannot say, look at, oh, this is an algae plant, what's the input, what's the output? That's not how you have to think. How can this input be, this output be an input to something else? You see the second part comes in. How can a waste of something be a food for another? How can an effluent of something be an input for something else? The other things already come into play. And then you have dematerialization component that we talked about. Instead of having something else from somewhere, how can we just use the wastes properly and then make much more reduced material footprint and then increased efficiency? All these things you see is enacted in an industrial symbiotic way. So what you could also do is that instead of this example, you could read another European example. Take any example and quantify it by scale. Maybe it's on a country level, maybe it's a park in itself. Find an industrial symbiotic example inside Belgium, and then tell me how these concepts, core concepts of industrial ecology, is applied there. That would be very interesting. So let's get into the exciting world of renewable energy. Renewable energy is an integral part of the transition towards circular economy, let's say. It is put forward as such by many of its proponents. One thing you have to notice is that, as we all know, a lot of emissions is related to energy consumptions and fossil fuels. So a transition towards renewable energy would be an essential and an integral part of the decarbonization journey that we have to make. Okay, having said all these things, as engineers or researchers, it's important to put numbers on things and to understand them as such. It seems like a daunting and a complicated topic, but I suggest that you read two books on this. One is Sustainable Energy Without Hot Air by Professor Mackay. This book is actually available for free for download. And I will give the link and you can download it for free. The other book I would say is to read Professor Václav Smil. Professor Smil has written many books on energy, but maybe the book Energy, the Beginner's Guide would be a good place to start. So what are we seeing in this slide? In the x-axis is the population density, and in the y-axis is the energy consumption per person per day. Okay, so as you could see, for a lot of European countries, France, Denmark, Germany, Netherlands, and even South Korea and UK, Japan, they are right at the top. So their energy consumption is quite a lot. I think for UK it's 125, and for Netherlands it's almost thereabouts. So you see also the blue lines here, right? The small blue lines which are indicating a transition or the growth from 1990 to 2005. And even for countries like India and Bangladesh, what you see is that there is an increase in population density, and also there is an increase in energy consumption per person. So this is almost the inevitable trend that has been seen for all the countries. So you could also imagine that in addition to fossil fuels, for almost a lot of the European countries and United States, there is the concept of embodied energy. So they import a lot of goods, which means that that too adds up in energy consumption. And then you have all these pink lines, the things that are descending down, and you could see it's in the measure of power consumption units, right? So it's watts per square meter. And why are they adding this line? It's quite an interesting thing. So you could see the UK and Germany is at maybe at 1.25 thereabouts, and almost more than 50% of countries are already greater than at 0.1 watts per meter square. This unit is interesting to add simply because of the fact that you could superimpose the units of renewable energy and then compare and contrast and then make conclusions. And that is the most exciting part. So in this slide, you see the green lines, the actual power per unit area for different types of renewable energy. So energy crops deliver almost 0.5 watts per meter square in European climate. What does it actually mean? It means that if you want to substitute, let's say, UK's consumption completely with energy crops, you have to cover almost the entire United Kingdom with energy crops. Maybe that's not a great idea. What about wind power? You have to almost cover maybe half of United Kingdom if you want to substitute the fossil fuel consumption that we have currently with that of wind power. So imagine, like, for a country which has 125 kilowatt hour per day per person, it's a lot to actually just switch off to a renewable, and then imagine that would solve the issue. Yeah, maybe as a population, people could accept 20 to 25% of their area covered by renewable energy, but that is going to be a steep task in managing the consensus of the whole population to come to the terms with half of their country covered with renewables. Maybe that's not going to happen. But it is important to know that there is an area concern. Solar parks, they give 5 watt per meter square, relatively higher, but you have to also understand that solar parks are not just individual panels. So you have the whole of the park, and then you have the gaps that contributes to the reduction in efficiency. In essence, the argument is that you have the renewables which are great instead of fossil fuels, but they are more and more diffuse, and then the energy that you could, the power is per unit area is quite small. The other thing that you have to also understand is that sometimes you have to put them in deserts. For instance, for tapping the solar energy properly, you have to put them in deserts, and I don't think all countries have deserts. So the diffusivity problem always exists for sustainable energy. So I want you to do the math. You don't need to deliver it as a homework maybe, but you have to do it for yourself, and maybe I'll open a forum where you can post. Pick any country of your choice. It can be Belgium, it can be some other country. Cover some percentage of its area with windmills. Please be reasonable. Do not cover maybe the entire country with windmills, so it doesn't make any sense. So give me an answer in kilowatt hour per day per person that you get from the windmills. Okay, so you know the wind power that I gave in the previous slide. Just give me an answer here. And then you compare that with an average 50-kilometer drive in a car for a kilowatt hour per day per person, and then tell me how it compares. It will actually be very illuminating to do these back of the envelope calculation. You don't need to be so accurate. You don't need to give me answers in decimals whatsoever, but do this calculation. It will really be interesting for you. Okay, so this will be the last slide on the renewables. This is a slide from Professor Varsha Smil's book. Professor Smil is somebody who puts always the larger picture in context, so it's very interesting to read him. One thing I would say again to emphasize is that road towards decarbonization would always involve renewable energy. It's an integral part of it. Switching to renewables is the key. But you have to be also reasonable with arithmetic, and only by looking at the numbers clearly you can put forward policy solutions properly. And having said that, for instance, if you want to replace a quarter of our fossil fuel derived energy consumption with woody biomass, you have to cover almost the entirety of EU and US forests. So that's not really that's not a probable solution. But also notice, if you are going to do that, what's the stress on other planetary boundaries, such as land use, such as, let's say, the water footprint and the loss of biodiversity. So you have to take into account all these things as well. And then if you want to, let's say, power all the US cars with corn-driven ethanol, then you have to almost take over the entire of US's farmland for that. That's another thing that you have to take into account. The solutions of biofuels has its own advantages and disadvantages. You have to also be cognizant of the fact that in future a lot will be talked about carbon capture and storage, CCS and BECCS. So for those things, have a close look at the land use planetary boundary. Okay, so and the other thing is that hydroelectricity has been put forward by many as an important renewable source. It of course is. There are a lot of plants in all over the world, and there are a lot of untapped potentials as well. But you may or may not know, recently, or for a past couple of decades at least, I would say, in Southeast Asia, especially in India, Bangladesh and other places, the mega projects have created a lot of resistance. There are multiple reasons for it. I don't want to go into the reasons, but the mega dam projects have faced a lot of resistance. So perception is also a key challenge. So, and the other thing is that wind energy is an important form of renewable energy, and if you tap it completely, you could almost get 6 terawatts for a particular period of time. But in terms of the modern demand, the spiking peak loads, integrating wind into the grid, and the soiling of lead blades, these are issues that remains to be addressed in terms of the wind energy. And sun is an unparalleled resource. It's an important resource, and moving on, solar energy and photovoltaics will be playing a key role. You have to also notice in those things that there are two disadvantages, I would say. One is the low conversion efficiency of photovoltaic cells, and the other is the high cost per unit. Okay, but these two things, disadvantages as they are now, may be due to technological improvement, can be solved in the future. Energy storage will be playing a really important role, very important role, because you know sun doesn't always shine, wind doesn't always blow, and then storing grid electricity is really the key. And batteries would play an enormously important role. A lot of people would tell you lithium batteries can be an important thing for energy storage in the grid. That is not actually a great argument. I can go into the numbers, but lithium batteries are a key in transportation. But for grid electricity storage, in terms of the cost, in terms of the energy density, and especially power density, those are two different things, by the way. For power density, it's really important to think about other type of battery systems. There are other solutions like redox flow batteries, liquid metal batteries, and so on and so forth. But anyways, energy storage still would remain the key. There are many things to be solved in the field of energy storage as well, but it remains really the key. But there is also a debate on the hydrogen economy. This is not something I'm going to go into in this lecture because it's a very complicated debate. Black hydrogen, green hydrogen, gray hydrogen, there are a lot of hydrogens and a lot of pathways in hydrogen economy as it remains. It's a very complicated subject. Maybe there is a possibility that I cover it in another lecture, but not for now at least. Okay, having said all these things, look for one commonality of what I'm talking about. These are all supply side solutions, okay? Production side solutions. What I clearly showed you from the last slide is that the power densities per unit area are small, and not every country is going to have everything. So you can put a photovoltaic cell or a huge solar park or whatsoever in a really windy and non-sunny location. It's not going to make a lot of sense. So it's a diffuse phenomena, and a lot of these things in the future would also be reliant on getting renewable energy from somewhere else. Countries might need to rely on other countries for renewable energy. That is going to be a key. So a solution portfolio is going to consist of many different things, including getting renewables from somewhere else, having multiple of these put together, not just one, investing in one type of renewable energy, but a lot of different types of renewable energy and a lot more different types of solution. Nuclear will also have to play a huge role because of how high the watts per unit area is. So a lot of these are going to play a role, and as you know, nuclear also faces a resistance for different reasons. But one thing we haven't talked about at all is that we have covered the production side. What about the other side? That is the demand one. That has a lot of importance, okay? So 125 kilowatt hour per day per person is quite a lot. So decreasing the consumption would go a long way actually together with renewable energy. So when we talk about renewables, just do not think that maybe we can switch completely to renewables and it will be solved, okay? Because you see the fossil fuel infrastructure may be around 20 trillions or so in budget in all over the world. So to completely overhaul the fossil fuel infrastructure is obviously going to face resistance from multiple interests, but also the technological challenge exists in the immediate switch to renewables, but we have to decarbonize fast. So reduction in consumption goes a long way. Then you have to understand as individuals, as nation states, what are the best way in reducing consumptions. Sometimes what we feel may not be entirely accurate or may not be enough. Maybe you feel that plugging off a charger of mobile phone would save a lot of energy. Is that true? That's something Professor Mackay answers in his book. It doesn't save a lot of energy. Instead, just reduce your thermostat. That could save much more. How do we know these things? We measure, we put numbers. Arithmetic would play a very important role in renewable energy. So I encourage you to read the book, and I encourage you to read a lot about different parts of renewable energy quantitatively and make up your own conclusions. A policy mix is going to have a lot of different angles, and I would encourage you to read a lot on renewable energy. So we come to the end part of the lecture 3. Then we will have lecture 4, which is an extension of Introduction to Circular Economy. There we will go into the butterfly diagram, the inner and outer loops, and performance economy. So you see, again, I didn't put biomimicry into this lecture, but both biomimicry and blue energy, I will give you links and you have to read by yourself, and then I'll open up forums where you can post what you learned to other people. So the social economy, the principles are fourfold. The first is placing service to the members or the community of a social economic system ahead of profit. So see, social economy can be operated in many different ways, like mutual aid societies as cooperatives, microfinance units in sometimes. In Southeast Asia, a lot of the social economic initiatives have been tried, and there are a lot of mutual aid societies even within a part of a governmental framework. And the second important thing is that autonomous management, mostly they manage themselves. They don't have a top-down structure, but a very equitable structure. And the third thing is democratic decision-making process. This is where it differs from other non-profit organizations. Maybe in other non-profit organizations, you have a rigid hierarchy. Here, they have a very democratic decision-making process. The fourth important thing is that they put the primacy of work and people over ROR, rate of return of their capital, actually. So there will be more or less equitable distribution of revenues and so on. But EC considers social economy to be important, but they put that these are the constraints to it, like they don't have access to capital, the recognition of such formality or forms are very low, mutualities and cooperations, and you don't have a lot of entrepreneurial skills, and the regulatory framework sometimes hinder social economy, is what EU or EC says. Having said all these things, it looks very promising, the social economy paradigm, but you have to also ask critical questions, as always, to social economy as well. Some proponents of CE, the circular economy, considers SE to be a part of it, but some may not. Essentially, it may or may not be in contradiction with each other, because CE in some parts considers economic growth at the heart of it. That means also you have to have profitability in a system as a part of it, but SE doesn't really put profitability at the very heart of it. So there are, let's say, not very smooth inclusiveness, but a little bit of tensions. But we will talk about these tensions, essentially a lot about growth in detail in the module where we have criticisms of circular economy. So having said all these things, one thing you have to notice is that EC's first constraint is very important: access to capital. So as long as you have large capital, you could think about solving huge magnitude of issues that we have. But if you don't have a lot of access to capital, then it means that maybe the social economy can be a part of the solution, but scaling it up can be a challenge in itself. So having said all these things, it brings an end to the lecture 3. So essentially try to work out one homework I gave. Second thing is also read about biomimicry and then post in forums what you learned about it, and also blue energy as well.